The worksheet looks harmless enough: cartoon apples, soft fonts, a cheerful instruction. Use the Make 10 strategy to solve. But watching a 5-year-old pause, furrowed brow, and try to remember which number they're supposed to break apart, something feels off. Not the kind of confusion that leads to discovery, but the kind that builds frustration. You can almost see the spark of number sense dimming under the weight of an unnecessary process. This isn't just overcomplication, it's miseducation. The child knew how to subtract, then they were told to do it the right way. In that moment, a simple truth gets buried beneath a method, and math, once intuitive and alive, becomes a set of steps to memorize. This is where it starts. This is broken kindergarten math. There's a troubling trend in mathematics education, particularly noticeable at the foundational level, in which educators attempt to simplify basic mathematical operations into rigid algorithmic procedures. At face value, methods like the Make 10 subtraction strategy are well-intentioned, designed ostensibly to ease students into arithmetic by breaking down calculations into more manageable parts. But beneath the surface, this approach may do more harm than good by fundamentally misunderstanding how intuitive mathematical reasoning emerges in the human mind. Let's first consider what the Make 10 method actually entails. To solve a simple subtraction problem, such as 13 minus 8, the approach mandates an explicit series of cognitive steps. First, identify how to get from 13 down to 10. Subtract 3. Next, break the original 8 into two parts, the initial subtraction, which is 3, and the remainder, 5. Then subtract the leftover remainder, 5, from 10, resulting in the answer, 5. Presented this way, what should be a simple mental leap instead becomes a 3-step algorithm, effectively replacing intuitive understanding with a strict procedure. While this might initially seem harmless or even beneficial, after all, isn't clarity helpful? It reveals a deeper pedagogical misalignment, treating the inherently fluid process of arithmetic reasoning as though it were a linear assembly line. This form of procedural reductionism not only oversimplifies, it risks transforming an intuitive, relationally driven cognitive process into an unnecessarily mechanical exercise. To better understand the shortcomings of this procedural strategy, consider arithmetic as fundamentally relational. Simple arithmetic facts naturally emerge from intuitive familiarity with numerical relationships, encapsulated neatly in logical triads of the form A plus B equals C. For instance, with the subtraction problem 13 minus 8, an intuitive mathematical thinker might instantaneously recognize that 8 splits neatly into 3 and 5, precisely because 3 complements 13 to form 10, leaving a comfortable and instantly recognizable remainder of 5. Expressed through a logical triadic structure, specifically a causal triad, recognizing basic numerical complements enables intuitive splitting of numbers, facilitating flexible arithmetic reasoning. Conversely, without intuitive familiarity, fluid reasoning and mental flexibility become difficult or impossible. Thus, what education should seek is to nurture this initial intuitive familiarity, enabling dynamic flexibility by way of internalized numerical relationships. Instead, current practices force students to work backward from the procedure itself. This approach imposes a different triadic logic, specifically a reinforcement triad. Following a prescribed procedure reliably produces correct answers, reinforcing adherence to the procedure itself. This reinforcement triad might initially seem benign or even effective, but its hidden cost is severe. Students learn to rely not on intuitive understanding, but on procedural compliance. When answers are correct, primarily because a procedure was correctly followed rather than understood, intuitive grasp of numerical relationships never fully develops, and genuine mathematical fluency stagnates. This procedural approach not only diminishes intuitive reasoning, it actively conditions learners into dependency. If math is experienced as something that demands careful, laborious effort, even at the most basic levels, then the calculator becomes a natural crutch rather than a helpful tool. Students internalize the idea that arithmetic itself is inherently cumbersome rather than a natural and straightforward cognitive operation. As a result, the cognitive effort once spent internalizing relationships is instead wasted memorizing procedures. When tasks inevitably increase in complexity, the absence of intuitive number fluency makes arithmetic seem insurmountable. Progress stalls precisely because the foundational relationships never truly solidified. What then would an intuitive, relationship-based model of arithmetic instruction look like? It would encourage exploration of numerical relationships, particularly triadic relationships, through playful, naturalistic experience rather than scripted algorithmic methods. Children naturally understand patterns and relational thinking when provided the chance to explore freely. By fostering genuine understanding of fundamental numerical complements and patterns, arithmetic becomes something intuitive, relational, and manageable. Rather than mandating a process, instruction would focus on cultivating the familiarity that makes intuitive splitting, decomposition, and recombination of numbers a natural, reflexive skill. Consider again 13 minus 8. An intuitive learner immediately sees this as an instance of complementary relationships. 13 breaks naturally into 10 plus 3, 8 naturally into 5 plus 3. This relational fluency is what should be nurtured, not the rote memorization of a rigid procedure. In short, the goal should not be to make math simpler by adding more steps, but rather to make it intuitive by building relational fluency from the ground up. The impulse behind methods like the Make 10 strategy is understandable. Educators genuinely aim to clarify concepts and facilitate understanding. However, they have approached the problem backward, mistakenly treating arithmetic as if it were procedural first and relational second. By imposing rigid processes on intuitive operations, schools risk conditioning students into dependent procedural mindsets rather than developing flexible, intuitive thinkers. A better way forward is clear. By cultivating intuitive number relationships from the earliest ages, education can reconnect arithmetic with its fundamental roots in relational thinking. Logical triads, representing dynamic, flexible mental patterns, can help guide educators toward methods that build genuine intuitive mastery. Mathematics is inherently relational, not procedural. Instruction should reflect this truth rather than distorting arithmetic into mechanical compliance.